You open your laptop, click a single button, and boom, you are connected to the world. We treat it entirely like magic.
Oh, absolutely. Or at least something we just completely take for granted.
Right. You don't think about the bizarre journey your keystrokes take to fetch a web page or, send an email. But today, we are decoding the invisible architecture, making that magic happen.
And it really is an incredible journey.
It is. We are tracing the data from the literal electrical current pulsing through the wall behind your desk all the way to the abstract, seemingly weightless realm of the cloud. So welcome to this custom-tailored deep dive.
Glad to be here for it.
Our mission today is to trace the exact physical and digital path of your data. We're uncovering the weird evolution of the networks we rely on every single day. Okay, let's unpack this. Let's start with the ground floor, which is the local area network, or LAN.
Yeah, to really grasp the scale of a modern LAN, I think it helps to start with the baseline of what you probably have in your own home or, a very small office.
The SOHO network. Small office, home office.
Exactly. In that environment, your entire network architecture is essentially consolidated into one little plastic box, one with a few antennas sticking out of the back.
And that single box is working overtime. I mean, it acts as a router to connect you to your internet provider, a switch to give you those physical wired ports, and a wireless access point for your phone.
Plus a firewall to keep malicious traffic out.
Right. It's the ultimate networking Swiss Army knife. Extremely convenient for a house or, say, a coffee shop. But when you look at how a massive enterprise campus network is designed, that all-in-one simplicity just vanishes.
It has to, yeah.
Instead of a Swiss Army knife, a corporate network looks more like a highly specialized, segmented factory assembly line.
That's a great way to put it. They use what is called a two-tier or collapsed core design.
Okay, break that down for us.
So you have access switches out at the absolute edge of the network. That is where the users actually plug in their computers.
Out on the factory floor, basically.
Right. Those access switches then feed into heavier-duty distribution switches sitting in the middle. The access switches form a star topology, meaning cables radiate out from the switch to the users.
Like spokes on a wheel.
Exactly. And then the distribution switches form a partial mesh topology to connect everything together. And actually, if it is a truly massive campus across multiple buildings, they'll add a third tier, a core layer.
A core layer? Why add another layer?
Primarily to minimize the amount of expensive fiber optic cabling they have to run into the streets.
Okay, I have to push back on this, though. If the SOHO router is so incredibly convenient, and it already handles routing, switching, and security all at once, why don't large enterprises just use giant SOHO routers? I mean, why bother with these complex multi-tier designs with hundreds of individual links?
Well, it really comes down to the brutal mathematical reality of network scaling. It is tempting to think you can just scale up a single device, but physical ports, silicon processing power, and the literal cables connecting them have hard limits.
So they just max out.
They do. Imagine an enterprise tried to connect every single switch directly to every other switch to ensure perfect redundant communication. We call that a full mesh design.
Sounds expensive.
Oh, the math breaks down almost immediately. There's an old networking formula to figure out how many cables you need for a full mesh. It's n times n minus 1 divided by 2.
Okay, let's test this. Say a standard office building has 42 access switches scattered across its floors.
All right, so if you multiply 42 by 41 and then cut that number in half...
I am definitely not doing that math in my head right now, but that has to be a massive number.
It's 861.
Wow.
Yeah. You would need 861 individual physical cables crisscrossing the building just to connect those 42 switches to each other.
That's absurd.
Right, and that also means 1,722 switch ports are consumed entirely just for the network to talk to itself, leaving way fewer ports for actual employees.
It becomes a completely unmanageable rat's nest.
Exactly. That is why the two-tier collapsed core design is brilliant. By funneling those 42 access switches into just 2 distribution switches acting as traffic hubs.
In a partial mesh.
Yes. You only need about 160 links. You maintain redundancy, so if a cable gets cut, the network survives, but you save hundreds of cables and ports.
You are bringing order to the chaos. And speaking of those access layer switches, the ones sitting at the very edge of this factory floor where we plug our devices in, they are doing something else that honestly feels a bit dangerous.
Oh, you mean PoE?
Yes. They aren't just sending digital data. They're sending literal electrical power. Power over Ethernet.
It's a game changer. Traditionally, network engineers just worried about data packets, and electricians worried about electrical voltage. Those were two totally separate worlds.
Never the twain shall meet.
Right. But PoE shifted that responsibility entirely onto the network.
Think about how this actually plays out in the real world for you listening. A switch, acting as the power sourcing equipment, sends direct electrical current down the exact same copper Ethernet cable that is carrying your data.
Which is wild when you think about it.
Yeah, it is. That is why your office IP phone, or the Wi-Fi access point mounted to the ceiling, doesn't have a bulky power brick plugged into a traditional wall outlet. It is drawing its electrical juice directly from the network switch in the closet.
Exactly.
But hold on, sending raw electrical power down a data cable sounds like a fantastic way to accidentally fry a laptop. Or like a printer that isn't expecting voltage to come through its network card.
Oh, if it was just raw power, absolutely. And that is exactly why the mechanism behind it is so elegant. The switch does not just blindly blast power down the line.
Yeah, it'd be good, miss.
It goes through a very precise, automated negotiation first. Before the connected device, what we call the power device, or PD, even boots up, the switch sends out a tiny, harmless trickle of voltage.
Just to test the waters.
Exactly. It is essentially testing the physical resistance on the copper wire. A standard computer network card won't react, so the switch knows to keep the power off. But a PoE-capable device has a specific internal resistor that reacts to that trickle.
So it's basically a secret handshake.
A handshake, followed by a negotiation. Once the switch confirms the device can handle power, they use Ethernet auto-negotiation to determine the exact wattage required.
Like, hey, I need this much juice.
Basically. The device effectively sends a message saying, I am a video conferencing phone, and I need exactly 15.4 watts to turn my screen on. Only then does the switch open the gate and supply the full power to boot the device.
That is surprisingly polite for computer hardware.
And the intelligence doesn't stop there. Even after the device boots, the switch constantly monitors the connection. If the phone goes to sleep, the switch dynamically lowers the power budget to save electricity across the whole building.
It's remarkably smart power management. So the next time you plug a laptop into an office wall or use a desk phone without a power cord, remember that you are interacting directly with PoE. You are utilizing this invisible dynamic power negotiation.
It's happening all around us.
But let's keep moving. So we've got hundreds of devices powered and talking to each other beautifully inside one building. But an enterprise isn't just one building.
Rarely, yeah.
If I have a headquarters in New York and a branch office in London, those local switches are completely useless on their own. How do we physically bridge that gap? We have to leave the LAN and enter the wide area network.
The WAN.
Right. And there are a few distinct ways to build this highway.
Historically, the simplest way for a company to cross a city or a geographic region is by leasing a service called Metro Ethernet, or Metro E.
Which essentially acts like a giant, invisible, physical cable spanning an entire city.
Pretty much.
And from our sources, there are three main flavors to this. E-line, which is a point-to-point connection, basically a dedicated digital pipe between two specific offices.
Yep.
Then there's E-LAN, which is a full mesh, letting any site talk directly to any site. And finally, E-Tree, which is a hub-and-spoke setup. Remote branches can only talk to the headquarters, not directly to each other.
Spot on. It is simple, it is elegant, and it feels just like your local network, only stretched over miles.
But here's where it gets really interesting. I mean, if Metro Ethernet is so straightforward, essentially acting like one giant switch, why would any enterprise tolerate the massive complexity of multi-protocol label switching?
MPLS.
Right, because MPLS sounds like an absolute nightmare of routing protocols, provider edge routers, customer edge routers, and label switching. Why not just use Metro E for everything?
What's fascinating here is that while Metro E provides fantastic simplicity at layer 2 of the network model, it treats everything like one big flat room.
Okay.
It doesn't give you granular control over the different types of traffic. A more complex layer 3 service like MPLS does. In fact, MPLS was the first WAN service to provide truly effective quality of service, or QoS.
Quality of service, meaning the network is literally playing favorites. It's looking inside the traffic and deciding who gets to go first.
Precisely. Imagine a congested 4-lane highway. Without QoS, every single packet of data is treated exactly the same.
It's a total free-for-all.
Exactly. If there's a traffic jam, everything slows down equally. Now imagine you have a live voice over IP or VoIP phone call happening on that network, while someone at another branch is simultaneously downloading a massive 50-gigabyte database file.
The voice call is going to start cutting out immediately. You'll get that robotic, delayed, jittery audio where people keep talking over each other.
Because voice traffic is incredibly sensitive to delay, jitter, and packet loss. A database file doesn't care if it arrives 2 seconds late. A human conversation absolutely does.
That makes sense.
So MPLS solves this through labeling. The customer edge router, the router sitting at your office, looks at that VoIP packet and stamps it with a specific QoS marking. The industry standard marking for voice is called DSCPEF.
DSCPEF, which stands for Differentiated Services Code Point Expedited Forwarding.
Say that 3 times fast.
No, thank you.
Yeah.
Okay, DSCPEF. How does that physically work? Is it a separate file?
Think of a packet of data as a physical envelope. The payload, your actual voice, is the letter folded up inside. The header is the routing address written on the outside of the envelope.
Okay, following.
Applying a DSCPEF marking is like slapping a bright red, fluorescent, urgent overnight delivery sticker right on the outside of that envelope.
Ah, so when it hits the service provider's network, they don't even have to look inside the envelope to know it's important.
Exactly. When the provider edge router in the MPLS cloud sees that DSCPEF tag, it physically bumps that voice packet to the absolute front of the processing line, skipping right past that 50-gigabyte database download.
Wow.
It guarantees low delay and low jitter. Furthermore, MPLS allows the service provider to use a protocol called multi-protocol BGP to redistribute routes.
MPDGP.
Yes. This allows the provider to create mathematically separated virtual private networks for hundreds of different corporate customers on the exact same physical routers, all without their data ever crossing streams.
So it's building a private VIP express lane for your most sensitive data.
That's exactly what it is.
So for you listening, if you have ever had a flawless, uninterrupted voice call with a colleague sitting on the other side of the country, you can thank MPLS. Those QoS markings prioritized your voice over someone else's giant email attachment.
It is invisible, but it's vital.
Truly. But we cannot stay on the highway forever. The data has to actually arrive at its destination. We've built the WAN highway to get our data to the data center.
But what happens when the data arrives?
Right, because the physical servers sitting in those massive air-conditioned rooms are not what they used to be. They have been entirely abstracted.
Completely. If you walked into a corporate data center a decade or two ago, you would see a strict one-to-one relationship. One physical metal server running one operating system, running one single application.
Very original.
Very. But today, the physical hardware, like those Cisco UCS blade servers sitting in their top-of-rack or end-of-row setups, are basically just raw, dumb resources. We refer to them simply as hosts.
And that is because of server virtualization. You have this magical layer of software called a hypervisor sitting right on top of the physical hardware.
Yes.
And the hypervisor's entire job is to decouple the operating system from the physical silicon. It takes the physical CPU, the massive amounts of RAM, the hard drives, the network cards, and it mathematically slices them up into virtual machines, or VMs.
So one physical blade server might be running 20 different VMs simultaneously.
That's incredible.
Each VM thinks it's a real computer, complete with its own virtual CPU, virtual network card, and even a virtual switch to network them together inside the box without ever hitting a physical cable.
That blows my mind a little bit.
And while that virtualization is incredible, it is only the prerequisite for the cloud. It is not the cloud itself.
I'm glad you brought that up. People use virtualization and the cloud interchangeably all the time, and they aren't the same thing.
Not at all.
For a virtualized data center to actually graduate and be considered a true cloud, it has to meet the 5 NIST criteria, NIST being the National Institute of Standards and Technology.
Right.
The first one is on-demand self-service.
Which is arguably the biggest revolution of the 5. Historically, the massive bottleneck in IT wasn't the physical hardware, it was the human beings managing it.
We tend to get in the way.
We really do. If a developer needed a new server to test an application, they had to submit a manual change request ticket to the IT department. Someone had to review it, approve it, physically rack the hardware, install the OS, configure the switch ports.
That sounds like it could take weeks.
It did. On-demand self-service means the developer just logs into a web portal, clicks a few buttons, and the virtualization software automatically spins up the VMs in minutes, without a single human administrator intervening.
Which perfectly feeds into the second criterion, rapid elasticity. Because the human bottleneck is gone, you can scale your application from 1 server to 100 servers over your lunch break to handle a spike in traffic.
And then shrink it back down to 1 server when the traffic subsides. If we connect this to the bigger picture, it changes how businesses operate entirely.
Totally. The third criterion is broad network access, meaning these resources aren't locked to a specific physical terminal in a basement.
Right. You can access and manage them over the network from a laptop a tablet, or a mobile phone using standard protocols.
Then there is resource pooling. Does that mean sharing the underlying physical hardware with other companies?
Often, yes. It is the concept of multi-tenancy. The cloud provider pools massive amounts of computing power together and dynamically assigns physical and virtual resources to multiple consumers based on demand.
So it's shared.
Exactly. You don't know exactly which physical blade server your VM is running on, and you might be sharing that physical processor with a completely different company. But the hypervisor keeps you strictly isolated.
Fascinating. And the final NIST criterion is measured service. Is that basically treating computing power like my monthly water bill?
That is the perfect analogy. The cloud system automatically controls and optimizes resources by metering them. You only pay for the exact amount of storage, processing, or active user accounts you consume.
Down to the minute.
Often down to the minute, or even the second.
So once a system hits all 5 of those marks, it's a cloud. But depending on what a company actually needs, they consume that cloud in different ways. We generally look at 3 main as-a-service models: IaaS, PaaS, and SaaS.
Infrastructure, platform, and software.
Right. I like to think of this through a real estate lens. IaaS, infrastructure as a service, is like renting a completely empty apartment. The cloud provider gives you the raw floor space, the virtual machine, the virtual CPU, the RAM, the storage.
You have to bring all of your own furniture.
Exactly. You have to install the operating system yourself, patch it, install the software, and maintain everything inside the walls.
And on the exact opposite end of that spectrum, you have SaaS, software as a service. This is like renting a fully furnished, all-inclusive luxury hotel room.
Oh, nice.
You don't worry about the plumbing, the electricity, or even making the bed. The cloud provider manages the underlying infrastructure, the operating system, and the application itself.
Think of something like Microsoft Exchange Online or Salesforce.
Yep. You simply log in through a web browser and use the finished software.
Which leaves PaaS, platform as a service, sitting right in the middle. This is like renting a professional contractor's workshop. The basic structure and electricity are there, but the workbenches are already stocked with very specific, highly specialized tools.
Which is great for developers.
Right. It is designed almost exclusively for software developers who need pre-supplied development environments, continuous integration tools, and databases. So they can just focus on writing code without wanting to manage the underlying operating system or, the empty apartment.
So to really clarify this for you, the listener, the cloud isn't just a marketing buzzword for someone else's computer. It is the highly automated, elastic, self-service nature of how that computing power is managed and delivered to you.
Whether you are renting raw infrastructure, a development platform, or a finished piece of software. But this massive shift toward consuming SaaS and IaaS creates a massive collision because companies are rapidly moving their internal apps out of their own private data centers and pushing them into these public cloud models.
And it causes chaos.
It does. Suddenly, those old WAN highways we just discussed, the ones carefully built with MPLS and Metro Ethernet to prioritize traffic between offices, are routing data to completely the wrong places.
It is a fundamental architectural conflict. You are describing the classic branch office routing problem.
Let's paint a picture of how ridiculous this gets. Imagine a company has moved from hosting their own email server in their basement to using a SaaS email model, like Microsoft Exchange Online.
Okay.
If Bob and Alice are sitting at desks right next to each other in a remote branch office in Ohio, and Bob emails Alice a 20-megabyte PDF presentation, what happens? In the old days, that 20-megabyte file traveled from Bob's computer across the private MPLS WAN to the central headquarters, hit the email server, and then traveled right back across the MPLS WAN to Alice's computer.
It wasn't wildly efficient, but it stayed safely inside the company's private network.
But now, with the email server living out in the SaaS cloud.
Now, you experience something called hairpinning.
Hairpinning?
Yeah. That exact same email from Bob to Alice travels across the private MPLS WAN from the Ohio branch all the way to the central headquarters. Then, because the email server is out in the cloud, the data exits the central site, travels out over the chaotic public internet to Microsoft's massive data center.
All the way to Microsoft.
Gets processed, travels back down the public internet to the central site, and then travels all the way back across the MPLS WAN to Alice in Ohio.
So what does this all mean? We just built this beautiful, expensive, QoS-enabled MPLS private WAN, and now the shift to the cloud is actively ruining its efficiency.
It really is.
All of our remote branch office traffic is unnecessarily bottlenecking at the central site's internet connection. We are literally paying for our own traffic jams, just so Bob can email Alice a file while they sit in the exact same room.
This raises an important question regarding the delicate balance between security and network efficiency. The traditional model forced all traffic through the central headquarters because that is where the massive, expensive corporate firewalls were located.
It was a deliberate security choke point.
Exactly. You could inspect every packet going out to the internet. But to solve the massive cloud bottleneck you just described, architects have to completely redesign the network. The most direct solution is to give every single branch office its own direct internet access, or DIA.
So just let the Ohio branch talk directly to the Microsoft Cloud over a local internet connection,
Right.
which instantly solves the hairpinning. Bob's email goes straight from Ohio to Microsoft and back to Ohio.
It does. But by doing that, you completely bypass the central security choke point at headquarters. So suddenly you have to rely heavily on placing robust firewalls at every single remote branch.
That sounds expensive, too.
It is. And you're using protocols like TLS or Cisco AnyConnect remote access VPNs to secure the traffic as it traverses the public internet. You are essentially trading expensive private WAN routing for public internet security risks.
But there is another solution that feels like the ultimate compromise: intercloud exchanges.
Yes.
It is essentially a private network as a service. Instead of putting raw, risky internet connections at every single branch office, your private MPLS WAN connects directly into an intercloud exchange facility.
And that exchange operates massive, dedicated, private, fiber optic connections straight into AWS, Microsoft, Google, you name it.
Right. It allows an enterprise to maintain those private QoS-enabled VIP express lanes directly into the cloud without ever exposing their data to the chaotic public internet.
It's the best of both worlds.
Plus, if you decide to fire your cloud provider and move your entire infrastructure from AWS to Google next year, the Intercloud Exchange just virtually reroutes the connection on their end. You don't have to dig up the streets to run new physical cables.
It is the ultimate abstraction of the wide area network. You are renting the routing just like you rent the servers.
And for you listening, this perfectly explains why enterprise networks, or even just the internet at your office, can sometimes feel weirdly complex or slow compared to your simple, predictable home Wi-Fi network.
It's rarely a hardware issue.
Right. It's not that the enterprise gear is worse. It's that your keystrokes and data packets are navigating these massive architectural routing challenges. They are constantly balancing security firewalls, QoS priority lanes, and the shifting physical locations of cloud servers.
It's a miracle it works as well as it does.
It really is. So, to summarize our journey today, we have traced the literal path of the modern digital world. We started at the edge of the LAN, where access switches use power over Ethernet to literally breathe electrical life into the physical devices around us.
All while negotiating multi-tier partial mesh architectures to keep the factory floor running without drowning in a sea of cables.
Exactly. And we watched that data jump onto the wide area network, where MPLS uses label switching and DSCP-EF tags to ensure your urgent voice calls don't get crushed by someone else's file download.
And finally, we saw that data arrive at the cloud,
where massive physical servers have been abstracted by hypervisors into virtual machines, instantly summoned by on-demand self-service portals, radically shifting how our networks have to route our daily traffic to avoid massive bottlenecks.
a lot to take in.
It is, but I want to leave you with a final concept to mull over. If server virtualization has completely abstracted the physical computer hardware, and the cloud has completely abstracted the physical data center, and now intercloud exchanges are abstracting the wide area network connections, at what point does the underlying physical hardware become completely invisible to the people actually running the world?
That's the real question.
And what happens to our digital society if we eventually forget how the physical foundation of those copper wires and fiber optics actually work?
A sobering thought to end on.